This problem gives us a magnetic field. I'll draw it in green directed into the screen. And it tells us that there's a copper bar with a length of 5 centimeters that's going to move perpendicular to this magnetic field. And it asks us how fast the bar needs to move to generate 1.5 volts across its ends. We can start by writing down the magnetic force on the free charges in the copper bar. That magnetic force is QV cross B. We can use the right-hand rule to see that on positive charges, this cross product is directed to the left. So as the bar moves in the direction I've shown, positive charges will be forced to the left, and negative charges will be forced to the right, and this sets up an electric field from the left to right direction. The force from that electric field is going to oppose the magnetic force. Charges will continue to accumulate until the electric field is strong enough that its force cancels the force of the magnetic field. We have an equilibrium situation when the sum of those two forces, the electric force plus the magnetic force, equals 0. They're in opposite directions, so their magnitudes will equal each other in equilibrium. QE, the magnitude of the electric force, will equal QV cross B, which is just QVB when everything is perpendicular, and we can cancel the charge Q. If we solve this for the electric field in equilibrium, we find that it equals the speed of the moving bar times the magnitude of the magnetic field. To find the motional EMF across the two ends of the bar, we can integrate the electric field from the left end of the bar to the right end of the bar. Assuming E is constant, we just get the electric field magnitude E times the bar length. Substituting our result from above, we see the motional EMF is VBL, the speed of the bar times the magnetic field strength times the bar's length. Now we can solve the question we were asked by solving for the speed of the bar, knowing the EMF, the magnetic field strength, and the length of the bar. When we substitute all of the values we were given, we find that the bar needs to move at 46.2 meters per second. And that works out to 103 miles per hour. So a bar of reasonable length needs to move really fast through a significantly strong magnetic field to have a voltage across the two ends equal to what we get out of a AA battery.